let's have a quick look of quick review of what we did on Tuesday. Now we begin. We are now in chapter 6, forces in structures, and the first type of structures we talk about is trusses. This is a truss, and the whole structure is a truss, and each rod is a member. Okay. Now, and the members are all forces are all members are two force bodies, and if we have one structure A, D, and B, so these are considered as two members, A, D, and DB. We don't have we are not talking about ADB. We are talking about AD and DB. And all external loads act on joints, and all external loads act on joints, for example, P, and we don't have forces like Q. We do not have forces like Q. And all joints are pinned, and it means DA and AB can rotate relative to each other. And if a member has weight, for example, 500 Newton, 250 Newton goes to the left and 250 Newton goes to the right. It's okay. Now, and we have a simple, and we have a relationship of number of members and number of joints. And in the examples we are doing, that usually this is correct. M equals to n minus 3. Now, and if m is larger than 2n minus 3, it is called statically indeterminate. This is what we have seen in chapter 4, and this means we cannot determine forces in all members. Now, for the SOP, for the procedure of analyzing trusses, the first step is for the rigid body analysis, same as chapter 4. Now, and in this problem, we have, I'll come back to this later, and we have a pin joint on the left and a roller joint on the right. Now, so because in a pin joint, we cannot move left and right, and we cannot move up and down. So we have a force in horizontal direction, and we have a force in vertical direction. And we have the original force P, and for roller joints that we can move to the left and the right, and we cannot move up and down. So we have one force going up. Now, and I think you can write these three equations down, and so we come to step 2. So for step 2, I will use my the notes I give you today. And in this new notes, and I'm drawing it more clearly. Okay, so who hasn't got the new notes? So let's go to the lower half of the page. And in the original problem, we have P here, right? Now we divide we are talking about a free body here. And of course, we have RAX, RAY, RAX, and then we have RB. We have RB1. RB. Now, and we have we are turning the free body into we are turning the truss into two free bodies. We are turning it into two free bodies, and so we have free body 1 and free body 2. Okay, we are turning it into two free bodies. Now, if we for this for free body 1, because this joint is pin, okay, this one is pin. For this for let's talk about 3.1 here. And for because this is point C, right? It's point C. This point C is P. So if we have a force P going downwards, that if we have a force P going downwards, that because this one is pin, then it will become this shape if we do nothing. If we do nothing, then the force will make this free body like this, right? It will go down like this. Now, if how should we get back to the original shape here? We add two forces here. Okay, so we originally it's like this, and because we have a force here, it goes downwards. And if we want to return the structure into the original position, then we add two forces here, add two forces here, and it will become the original shape, right? Now, so how much force do we add to the original shape? Now we look at this figure. Now, if we come back to the original shape, for this force, for these two forces, and by action and reaction, the forces acting on free body 2 is the same. By action and reaction, if these two forces are T, these two forces are T as well. Because this free body 2 is actually it is structure AD, right? AD. So we mark this tangent as TAD. By action and reaction, we have these forces also as TAD and TAD. Is that okay? So let's go back to the after drawing this page, drawing on this page. Please go back to the original. Please go back to the original notes and let's go back here. So this comes to this figure we are having here. It's okay. Now, and we say we are cutting, we are dividing the truss into two free bodies by cutting this along this line. So we do the same, we use the same method to cut these two. It's okay. We use the same method to cut the structure into, we cut free body one into two and like this. So you can repeat the whole thing, and what do we have now? Originally, because we have TAD here, right? TAD, TAD, and now we have here. If we cut along AC, we can have TAC here and TAC here by the same method or by the same principle. By the same principle, we have we can draw it like this. So we have two free bodies, two rigid bodies now. Let me call them rigid body A and rigid body B, C, D. So and so because it is in equilibrium, go ahead, take some time to draw it first. Now, for rigid body A, it is only a point, because it is because the whole truss is in equilibrium. So we have this part will have equilibrium, and this part also have equilibrium. So how many equations do we have? Let's take a look. On the left, rigid body A. On rigid body A, we have because it is a point, so we have only two equations. F(x) equal to 0, Fy equal to 0. And for rigid body BCD, it is not a point, it's a rigid body, it can rotate. So we have three equations. In this system, RAY is known, RAX is known, RB is known. How many unknowns do we have in this system now? Because in the first step, we know, let me go back to step 1. In step 1, we know the quantities RAX, RAY, and RB. These three are determined in step 1. Now in step 2, in these two free body diagrams, what are the unknowns? Or how many unknowns do we have? P is known, RB is known, RAY is known, RA is known. So how many unknowns do we have? Or what are the unknowns? The unknowns are TAB and TAC. So we have two unknowns, so we only need two equations to solve the to determine the unknowns. So we would calculate we would determine TAT and TAC using this method. Now, and the same can be done for. Sorry. Now, and the same thing can be done on all joints, and you can remove this part, and you can remove this part, and then we will arrive in another rigid body here. Rigid body T. Now, for this course and in the textbook, we have method of joints and method of sections. We are using method of joints in this course. In the textbook, we have a map of joints and map of sections. We are using map of joints in my course. And okay. Now, and so we can do, of course, we get this by a long, we get this bridge body after only 2 hours. But of course, after you know the principle, the other joints can also be drawn quickly. So I have two. For example, if we cut this part and we cut this part, then we will arrive in this joint D. And for this joint D, and so how should we draw the free body diagram? Now we have force P on joint D. And because we have, and to the left of joint D, we have what? We have joints. To the left, we have what do we have on the left of D? We have A. And to the right, we have B, and on the top, what do we have? What do we have on top of on top of D? Point C. So we have, and by the same method, we can have TAD. This is given here, and using the same method, and we have TBD, and we have TCD. From here to here, that we are using the same principle, and after you go home or this weekend, try to see, try to look at this again, and see if you have any questions. Now, and I have three things for you. Of course, in this kind of process, we want to determine if these forces, if we have forces in these members. For example, do we have force in member AB? Do we have force in member AC? Or we have members? We have force in member BC, for example. And so what we calculate is these members can have what do we have? We can either have tension or compression. And these are, I would say, this. And we have either tension or we have compression, because we have two force bodies, and we can either only pull it or press it. Make it 0.1 here and 0.2 here. if we have so in these calculations, if we if the result is t is positive, which is t is greater than 0, it means the member is in tension. And if t is smaller than 0, it means we have compression. And this is the first thing. So after our calculation, we will get numbers either larger than 0 or smaller than 0. If it is larger than 0, it means, for example, if we get T8 is larger than 0, it means this member is under tension. Now, and if we have to get this, we at the beginning of calculation, we assume all members are under tension at the beginning. So I will show examples to you, and I'll show examples to you, and all members are assumed to be under tension at the beginning. The second thing, the last point. You may think it is how should we do this? How should we do this? Or how should we keep this right? And to do this, it's very simple. In a free body diagram, of a node, all these member forces are pointing away from the node. Let me write in Chinese here, and I'll write in English. Here. Okay. So in a free body diagram, these member forces are always pointing outwards, or you can say away from the node. I'm sorry, away from drugs. It's okay. Of course, you may ask what am I doing here? So let me go to an example. After you write this and go to the next page, and I'll give you an example. After you finish writing this page, and go to the next page, and I'll give an example. now we go to the next page. So for this truss, and the question is to determine the force in each member of truss. It means we need to determine 1, 2, 3, 4, 5, 6, 7. The forces is we have 7 forces to determine. Now we have so for the first 2 steps and for, to solve this problem, we have the SOP. The first step 1 is to determine the support forces, and we have a pin joint here and we have a roller joint here. Now I think because we don't have much, and I think we go back to I go to the notes I gave you today, and let's have a look of the 2 most common supports we have in statics, in mechanics, and for a pin support, it means for a pin support, it means we can rotate. We can rotate, but we cannot move. We cannot move to the left and to the right, and we cannot move up and down. It means something. If I fix my elbow here, and it means we can rotate here, but we cannot go up and down, or we cannot go left and right either, but we can rotate. Okay. And for roller supports, it means we can rotate, we can go left and right, and we cannot go up and down. These are the 2 most commonly used support conditions in the mechanics. And for these 2 types of supports, different books would use different symbols. We have different symbols. Different books will use different symbols for these 2 types of supports. So for pin support, we have the 3 types on the left. Some books use this one, and some books use this one, and some books use this one. They are all the same thing. And for roller supports, of course, I think when I discuss chapter 4, and I use this, but in some books we have this, and in some books we have this. They are all the same thing. It's okay. So, and if you're okay, then we go back to sample problem 6.1. Now for the first step, and we draw the three-body diagram of A, B, C, D, E, the whole structure. And because of the time, because I don't have time now, and can you do it at home? Can you do this at home? And this is figure one of page 309. But first of all you draw the three-body diagram of A, B, C, D, E, the whole structure. And then from this three-body diagram of A, B, C, D, E, and we can write three equations, and we will get these three. We'll get all the support forces. Okay. Please, I will leave this for you as I will. And to study this part. And this is actually coming from chapter 4. The same as chapter 4. Now for the next, so we go to the next part, which is step 2. We want to get the force in each member. So I'm showing you joints A here. Joints A. So consider equilibrium at joint A. And today I will draw the three-body diagram, and on Tuesday I will talk about the next steps. So at joint A, what do we have? We have one force of 10 kilonewton to downwards. Afterwards, and the next step, which members connects to joint A? We look at this figure. Joint A is here. So what are the members connecting joints A? What are the rods or what are the things that connects with joints A? We have AB here, right? And AB. So we have two. So we have AB here and AD here. Now remember what I said. And forces, these member forces are going away from the joints, So this is TAP, and this is TAD. And of course, we have an angle freedom here. So I think I'll stop here and I will have some quick explanation.